Sound is everywhere. It's all around us, all the time, from the quietest little whisper to a huge, deafening roar. But what is sound, really? In this explainer, we're going to dig into the fundamental physics of how it all works. So let's jump right in.
So let's kick things off with a question for you. Think about a buzzing bee, the sound of my voice right now, and a ringing bell. I mean, they sound completely different, right? But on a physical level, they all share the exact same starting point. What could it be? And the answer is vibration. Yep, that's it. That's the one thing that ties it all together. Every single sound you have ever heard, from a bee's tiny wings flapping to your own voice, it all begins its journey as a simple vibration. It's the spark that gets the whole process started. Okay, so we're throwing this word vibration around, but what does that actually mean? To really get a handle on sound, we have to understand this core idea. And it's not some vague concept. It has a very clear physical definition. Just picture this. You pull back a stretched rubber band and let it go. That super fast back and forth wiggle, that is a vibration. Your own vocal cords are doing the exact same thing as I'm talking. That physical movement is the absolute key. It's what kicks everything off, turning motion into the energy that our brains eventually process as sound.
All right, so we've got a vibrating object. Cool. But how does that vibration get from, say, a guitar string all the way across the room and into your ear? It doesn't just teleport there, it has to travel. And the way it does that is by creating waves.
And this is the really critical thing to get. Sound needs something to travel through. It needs a partner, what we call a medium. That could be the air we're breathing, the water in a swimming pool, or even solid steel. Without a medium, sound is stuck. It can't go anywhere. That's why the old saying is true. In the vacuum of space, no one can hear you scream. There are just no particles out there to pass the vibration along.
So how does this energy transfer actually work? You know the best way to picture this? A slinky, seriously. If you push one end of a slinky, you see that wave of energy travel all the way to the other side, right? But each individual coil just kind of wiggles back and forth. It doesn't actually travel down the line. That is exactly how sound works. The vibration starts a chain reaction, but the air particles themselves are just playing a game of tag, bumping into their neighbors and then returning right back to where they started.
So as this disturbance travels, it creates this really cool pattern. When the vibrating object pushes forward, it squishes the air particles together, creating a little zone of high pressure. We call that a compression. And then when it moves backward, it leaves behind an area where the particles are all spread out, a low pressure zone called a rarefaction. So sound is literally just a traveling wave of these squished and stretched out parts of the air. And when you put all that together, you get the official scientific name for it. It's called a mechanical wave because it needs that physical medium to travel, and it's a longitudinal wave because the particles vibrate back and forth in the same direction that the wave is traveling, just like our slinky.
Awesome. So now we know what a sound wave is, but how do we tell them apart? How do we describe the difference between, say, a really deep bass note and a super high-pitched whistle? Well, we use 3 key characteristics to decode any sound wave. First up, let's talk about wavelength. The easiest way to think about this is to imagine you could just hit pause on a sound wave, just freeze it in midair. If you were to measure the distance from the middle of one of those squished up areas to the middle of the very next one, that distance, that's the wavelength. Okay, so if wavelength is about distance, our next one, frequency, is all about time. Imagine you're standing in one spot and the sound wave is just passing by you. The frequency is simply how many of those complete waves, or those squished up compressions, pass by you every single second. And we measure that in a unit called hertz. And the last piece of the puzzle is amplitude. This one is all about power. It's the oomph behind the wave. It tells us how much of a disturbance is happening. How tightly are those air particles getting squished together? A wave with a big amplitude is a high-energy wave, and it's making a much bigger scene. Okay, so this is where it all clicks together. This is how the physics connects to what we actually hear. Frequency is what our brain understands as pitch. So a high-frequency wave, one with lots of waves passing by every second, sounds high-pitched, like a flute. An amplitude, that's what we perceive as loudness. A wave with a huge amplitude is carrying a lot of energy, and it sounds loud, like a clap of thunder.
All right, enough with the theory. Let's talk about how this stuff actually works out in the real world. Because this isn't just something in a textbook. It governs everything from the way a concert hall is designed to the echo you hear when you shout in the mountains.
So I've got a question for you. Think about it for a sec.
We know sound needs a medium to travel through, but does the type of medium change its speed? Where do you think sound moves the fastest? Through a gas, like air, a liquid like water, or a solid like steel?
Yeah, it's not even close. The difference is absolutely massive. Sound travels through steel more than 17 times faster than it does through air. And the reason is pretty simple when you think about it. The particles in a solid are packed together so tightly that they can pass that vibration along to their neighbors super quickly and efficiently.
So sound waves don't just go in one direction and then vanish. Nope, they bounce off of things. Just like light bouncing off a mirror, sound reflects off surfaces. When you get one single, clean reflection, we call that an echo. But when you're in a big empty room and you clap your hands, you hear thousands of reflections all bouncing around and mixing together. That jumbled, lingering sound is called reverberation, and architects have to be super careful about controlling it when they design places like concert halls.
You can actually use this to do some cool real-world math. Let's say you're standing near a huge cliff and you clap your hands. If you hear the echo exactly 2 seconds later, how far away is that cliff? Well, the sound had to travel to the cliff and then all the way back to you in those 2 seconds. We know sound travels at about 346 meters per second in air, so the total trip was about 692 meters. That means the cliff has to be half that distance away, so 346 meters. Pretty neat, right? Okay, so we've talked a lot about the sounds we can hear, but honestly, one of the coolest parts about sound is the whole world of it that we can't hear. Our ears have some pretty serious limits.
So you can think of human hearing as being stuck in this little Goldilocks zone. We can usually hear frequencies from about 20 hertz on the very low end, all the way up to about 20,000 hertz on the high end. Anything that vibrates slower than that is called infrasound. It's so low, it's more of a rumble you feel than a sound you hear. And anything above our range, that's ultrasound, vibrating so fast it's completely silent to us.
And this is where things get wild because the animal kingdom is playing a totally different game. Elephants can communicate using that super low infrasound over huge distances. Even earthquakes produce it. On the flip side, animals like bats and dolphins use high-frequency ultrasound as a kind of built-in sonar system, which is how they can navigate and find food in total darkness. And that kind of leaves us with this one big final thought, doesn't it? We're living inside this one tiny slice of the entire acoustic world. The air around us is buzzing and rumbling with all kinds of conversations and information that our senses are completely blind to. It really makes you wonder, what else might we be missing?